This term we're going to be looking at compounds containing the carbonyl group. That's the C double bond O group here. We're going to be focusing in on reduction, the mechanism with which they react, and also looking at how we can arrive at a form of isomerism called stereoisomerism. Let's now take a look at the carbonyl group itself, the C double bond O. What's not really studied at AQA is the nature of the C double bond O, that the carbon double bond oxygen is in fact two different types of bonds. There's a pi bond and a sigma bond. Also, it's a planar molecule. Let's look at the pi bond. The pi bond is formed by the sideways overlap of two p electrons, one from the carbon atom and one from the oxygen atom, and it's slightly weaker than the sigma bond. As I said, it's not really covered at AQA, but it's useful to note that this pi bond, the second bond, is the one that breaks, and the pi bond is represented as this cloud of electrons that lie above and below the plane of the sigma bond. Sodium borohydride or sodium tetrahydroborate is a powerful rich source of hydride ions, H- ions. Hydride ions are nucleophiles and they're attracted to the electron-deficient carbon in the carbonyl compound. They attack, donating a pair of electrons, forming a dative covalent bond, and at the same time the pi bond pair of electrons moves onto the electron-deficient oxygen, resulting in a negative charge. So the dative covalent bond that's formed with the hydride ion results in an intermediate with a unstable negatively charged oxygen. Any protons or surrounding water molecules are quickly attacked by this negative charge, and a proton is taken either from water or from any acid. Notice it's the lone pair of electrons on the oxygen that are donated to the hydrogen. The resulting molecule is an alcohol. So in effect, it's the reverse of oxidation. This is a reduction reaction. The mechanism, because the molecule was attacked by a nucleophile, is nucleophilic. So the role of the hydride ion is a nucleophile. And because it's gone from 3 groups to 4 groups, it's undergone an addition reaction. So the mechanism we call nucleophilic addition. The reaction type, because we've added hydrogen, is a reduction reaction. Here's a general equation for the reduction using hydride ions. So you never write in the full formula of the sodium borohydride or the sodium tetrahydroborate. You simply represent it as the H- ions. So in general, the aldehyde or ketone is reduced to an alcohol. So it's important to know at this point the difference between the mechanism and the reaction type. The mechanism is nucleophilic addition. So this is the mechanism, whereas the reaction type, because we're adding hydrogen atoms, is a reduction reaction. So nucleophilic addition is the mechanism, reduction is the reaction type. This next exercise, we're going to write mechanisms for the reaction of the following compounds with the sodium borohydride: propanone, which is a C3 compound, methanol, which is a C1, and pentanone, which is a C5. So first of all, let's draw the structure of propanone. And the best way to draw the mechanism is to show the bond angle around your planar ketone in this case. So show the 120 degree bond angle. So here is the hydride ion with its lone pair of electrons attacking the electron deficient carbon and the pair of pi electrons moving onto the oxygen. So it's really important, put in your dipole here so you know why the hydride ion is attacked. The resulting intermediate is now going to have a bond angle of 109.5 degrees. Here we've just shown it in the 2D format. We've now got a single bond oxygen as a pair of electrons which are represented here. These are the pi electrons have moved on to the oxygen. This pair of electrons now is donated to the hydrogen in a water molecule. And don't forget that if a pair of electrons is moving to the hydrogen, this bond also has to break and the pair of electrons from this bond move onto the oxygen. The resulting molecule, as you can now see, the oxygen has gained a hydrogen atom here from water. The hydrogen that came from the sodium tetrahydroborate is attached here. And the resulting molecule is an alcohol, a secondary alcohol, propantuol. Don't forget the rest of the water molecule, which is left as a hydroxide ion. Let's now look at methanol. Again, exactly the same mechanism. Put your dipole in. The hydride ion attacks the electron deficient carbon. The pi electrons move on to the oxygen. The intermediate shows the oxygen with a lone pair of electrons that have come from the pi bond. This is really, really important. Put your lone pair of electrons on there. There's the original hydrogen, and here is the hydrogen that's come from the hydride ion. This intermediate then completes the reaction by picking a proton off a molecule of water. Again, show the pair of electrons coming from the bond forming from the pair of electrons and then moving onto the oxygen atom. The resulting molecule this time is a primary alcohol. And the primary alcohol, you can see, has got one carbon. There's the OH group. So this primary alcohol is got one carbon. So this is methanol. In the next reaction, we're going to look at pentan-2-one. But it's quite cumbersome to draw the whole molecule out when you're writing out mechanisms. So we're going to use a little trick where we put this part of the molecule, represent that as R for the rest of the molecule, and this methyl group here as R dash. So it's a lot easier to see the mechanism. It takes you a lot less time to draw out the mechanism. So the mechanism is going to be identical to the ones before. The hydride ion, the nucleophile, attacks the electron deficient carbon atom. The pi electrons move onto the oxygen. And the intermediate with the oxygen with a negative charge, it's a lot simpler to draw with the R, the rest of the molecule is identical to the ones that we've looked at before. So here's a lone pair of electrons that have now moved on to the oxygen. There's our hydrogen atom attached from the hydride ion. So this pair of electrons now removes a proton from water by donating the pair of electrons originally from the pi bond. The covalent bond between the hydrogen and the oxygen breaks as the electrons move onto the oxygen. So the resulting species, again, is an alcohol. We leave the R groups on for now to show the whole structure of the alcohol. And what we can now do is draw the whole molecule out following the mechanism, substituting back in the alkyl groups. This is it's a little trick when you're asked to draw a mechanism with quite large molecules. So we now simply put our dash on, which was CH3, and we put the R group on, which was the propyl bit. And if we now count the number of carbon atoms, the longest chain is 5. The OH group is on carbon 2, and that is pentan-2-ol from pentan-2-one. So it's a secondary alcohol from a ketone. So to summarise, aldehydes, when they undergo reduction with sodium borohydride, when they are reduced, produce primary alcohols. And remember from alcohols, primary alcohols, when they undergo the opposite of reduction, undergo oxidation, and the oxidizing agent was acidified potassium dichromate. So the opposite of reduction is oxidation, and the reagent for oxidation is acidified potassium dichromate. So aldehydes get reduced to primary alcohols get oxidized back to aldehydes. Now if we look at ketones, when they undergo reduction form secondary alcohols when they're reacted with sodium borohydride or sodium tetrahydroborate. So, and conversely, when secondary alcohols undergo oxidation, so reduction, ketones form secondary alcohols get oxidized back to ketones. Now we're going to look at another nucleophile. So we've met the hydride ion, and this is the cyanide ion. Cyanide ion is extremely toxic. However, it's essential in organic synthesis for what we call ascending and homologous series, increasing the number of carbon atoms as you go up an homologous series. And it's probably the only way to do it in aliphatic chemistry. So it's creating a new carbon to carbon bond. So this synthesis is carried out in fume cupboards as the cyanide ion is extremely toxic. And if we draw out the full structure of the cyanide ion, you can see it's got a C triple bond N. Now in this reaction, it's hydrogen cyanide which attacks, but it's a lone pair of electrons coming from the carbon atom which attacks the carbonyl group. Now in this mechanism, because this is a planar molecule, the nucleophile, in this case the cyanide ion, can attack from above or below the plane of the carbonyl group. So it can come from above or it can come from below. And what you end up with is a mixture of two molecules which look identical, but they're actually not. They're mirror images of each other. So the nucleophile, because it can attack from above or below the planar carbonyl group, results in two isomers which are mirror images of each other. And we're going to have a look at three-dimensional representation of them in a moment. The name of these mirror images, these molecules, or anything that has a mirror image of itself, is called an enantiomer. So we end up with a pair of enantiomers. Let's look at the mechanism and the reaction between ethanal and hydrogen cyanide. The pair of electrons comes from the carbon as the hydrogen cyanide dissociates. And as we saw in the nucleophilic addition mechanism with the hydride ion, this time we're going to use 3D representation. So there's our cyanide ion added on. There's our oxygen with a negative charge and the lone pair of electrons coming out of the plane. And behind you can see the hydrogen atom here. So we've got a 3D representation showing the tetrahedral arrangement from the trigonal planar arrangement. So the molecule we end up with is a tetrahedral shape, and so in the same plane as the methyl group here and the what we call the nitrile group, the hydroxyl group of the alcohol is coming out and the hydrogen atom is behind. The name of this molecule is 2-hydroxy 1,2,3 propane, because the longest chain is 3 nitrile E, because nitrile is an N. Now here we have the 3D representation of 2-hydroxypropane nitrile, and here we have its mirror image in this molecule here. So these two molecules are identical apart from the fact that the atoms are arranged differently in space. So we call these molecules optical isomers, and we'll be looking at optical isomerism as a whole topic on its own later. So these molecules are identical apart from the fact that the atoms are arranged differently in space, and this arises when you have 4 different groups around a carbon atom, and we'll be looking at this later in the topic on optical isomerism.